Good day, students. Today, our topic of discussion is interference of light and an instrument that makes use of interference of light, that is Michelson's interferometer. It is a very important instrument that has been in use for several decades. Now, the picture shown here shows an important discovery made using this Michelson's interferometer. Try to identify this. We shall come to it at the end of this session. Now let us see what a Michelson's interferometer is. It is an instrument that uses interference of light to make precise measurements of wavelengths or distances. So it is an instrument that is used to make measurements. Measurements of what dimension? Measurements of wavelengths or distances. That is precise, very small measurements. Now this is the basic diagram of a Michelson interferometer. We have light emerging from a source, and this is split into two by means of a beam splitter. So light is partially reflected and partially transmitted. So we have division of amplitude, two beams are formed. Now both of these beams, they travel the same path towards the mirror. Okay, so the mirrors are kept at equal distances but perpendicular to each other, and the light gets reflected from these mirrors. Okay, so they reflect back and happen to fall on the same beam splitter. There, these two light rays interfere and produce an interference pattern. So this pattern can be observed in this direction. Okay, so if we place a screen here, the screen shows an interference pattern, or we can view the interference pattern through a telescope. A beam of light from an extended source is divided into two parts of equal intensities by partial reflection and refraction. The beams travel in mutually perpendicular directions and come together after reflection from the plane mirrors. Now, what are the basic components in a Michelson's interferometer? So this is the basic setup of a Michelson's interferometer, an MI, in a laboratory. So you can see that all of these are set in a small scale. Now, the first component is the extended light source. Usually it is a laser source. Here we have used a green laser source. Okay, so this is the first component. This is the laser source that we have used. Next is a beam splitter in ratio 50:50. That is, light is reflected and transmitted in equal percentages of 50%. Okay, so 50% light is reflected and the other 50% is transmitted. Okay, and here we have this beam splitter. The next component is a compensating plate with the same thickness of the beam splitter. It is a glass plate with the same thickness of that beam splitter, and it is optional. Here in the laboratory setup, we have not used the compensating plate. Now next is the two plane mirrors that have high reflectivity. Okay, so 99.99% reflectivity should be seen for these plane mirrors. And we have the two plane mirrors here. One of the mirror is here and the other mirror is here. Okay. And the next component is the screen or the camera or the telescope where we can detect or see the fringe pattern. Okay, so these light beams, they are divided into two here, fall on the mirrors, come back and happen to interfere here, and this pattern can be viewed in this direction on the screen. Now this component is actually a convex lens that helps to magnify the interference pattern. Now, what is the working of a Michelson's interferometer? So we have this basic diagram again here. S is the source light. It emits the monochromatic light, and we can make it parallel by making use of a convex lens here. So we get a parallel beam of light, and this parallel beam is allowed to fall on a beam splitter here named as G1. Okay, so when light falls on the beam splitter G1, uh, notice that it is falling in the bottom surface of this beam splitter. Light is divided into two. The reflected portion is represented by the green ray, and the refracted portion is represented by the red ray. Okay, now these two rays travel equal distances and get reflected by two mirrors, M1 and M2. Okay, M1 and M2. And the reflected rays from these two mirrors, they again fall on the beam splitter and interfere. The interference pattern can be thus viewed in this direction on a screen or any detector like a camera or telescope. Now, this interference pattern can also be viewed in this direction. Okay, but here already we have the source, and if we place a detector here, it will block the source and no light rays will be falling in the beam splitter. So if there is no light, there won't be any interference pattern. Okay, so usually we never place the detector here because it may block the source, and hence we use this position to read the fringe pattern. Okay, so here monochromatic parallel light rays are incident on the beam splitter. Light is partially reflected towards the mirror M2 and partially transmitted towards the mirror M1. Now, since we have two beams, one of the beams will be always taken as the reference beam and the other will be taken as the object beam. Now, the reference beam will be kept stationary, whereas any changes or any measurements are done in the object beam. Here, let us consider the green lines or the green rays to be the path of the reference beam and the path of the red rays to be the object beam. Okay. Now, a compensating plate is used usually to compensate for the additional path traveled by the ray towards M2. Now, I asked you to notice that light is passing through the beam splitter and getting divided at the lower surface. So here light falls upon the beam splitter, it enters into the beam splitter, and as it falls on the lower surface, it gets divided. The transmitted beam will have entered into the next medium, whereas the reflected beam again travels through a small distance, that is the thickness of the beam splitter, and then emerges out. Okay, so it has traveled an additional path here, then it moves towards the mirror, gets reflected, comes back, and again it travels an additional path. So the additional path traveled in the beam splitter is 2 mu t, where mu is the refractive index of the beam splitter and t is its thickness. Now this additional path is compensated in the compensating plate. The transmitted light represented by the red rays, while in this direction it travels the thickness t, and after reflecting from the mirror M1, again it travels through this plate of thickness t. Hence, the additional path difference of 2 mu t is compensated, where mu is the refractive index of the compensating plate. It will be identical to that of the beam splitter, and t is again thickness of the compensating plate, which is identical to that of the beam splitter. The light rays get reflected from the mirrors and superimpose at the beam splitter to form an interference pattern. The fringe pattern can be viewed on the screen or it can be recorded using a camera. And this will be the nature of the fringe pattern. If the light intensity is low, this fringe measurements can also be done using a telescope to view the. So the additional path traveled in the beam splitter is 2 mu t intervented. So the additional path traveled in the beam splitter is 2 mu t, where mu is the refractive index of the beam splitter and t is its thickness. Now this additional path is compensated in the compensating plate. The transmitted light, check. The transmitted light represented by the red rays, while in this direction it travels the thickness t, and after reflecting from the mirror M1, again it travels through this plate of thickness t. Hence, the additional path difference of 2 mu t is compensated, where mu is the refractive index of the compensating plate. It will be identical to that of the beam splitter, and t is again thickness of the compensating plate, which is identical to that of the beam splitter. In this case, you can see the exact center of the fringe pattern. That is, you can see circular fringes. Now, whereas in the second case, if these mirrors are tilted with respect to each other, okay, you will be seeing localized fringes that are alternate, bright and dark, straight fringes. Okay. Now the circular fringes are produced when the mirrors M1 and M2 are exactly perpendicular to each other. Localized fringes, as shown in B, are produced when the mirrors M1 and M2 are tilted to each other. Now, if we use a white light source instead, okay, so till now we had been discussing of using a monochromatic source light, a single wavelength source light. Now, instead of that, if we use a white light source, what do we see? We will see a few colored fringes, and it may be just 10 or 12. Here I've written just 8 to 10 colored fringes. That is very small number of fringes with a central dark fringe. Okay. Now this is helpful if we need to determine the exact position of zero path difference. And the fringe pattern will be in this nature. It is extremely difficult to obtain this fringe using white light. So while doing the experiment, we have to take extreme care, because this will be obtained when we range the mirror through a few micrometers. So that we have to be very precise in shifting the mirrors to obtain this fringe pattern. Now let us use this Michelson's interferometer to measure the wavelength of the source light used. So we have this apparatus arranged in such a manner. The monochromatic parallel light rays are incident on the beam splitter. Light gets partially reflected towards M2 and partially transmitted towards M1. The light rays then get reflected from the mirrors and superimpose at the beam splitter to form an interference pattern. Now the fringe pattern can be viewed on the telescope, and further measurements are done using the telescope. Now here I have mentioned that let this path be the reference beam and this path be the object beam. Now we do certain measurements using the object beam. One of the mirrors, that is in this figure, we have the mirror M2, is moved through a known distance d, that is d2 minus d1, to produce a path difference. Okay, so if initially the mirror 2 was at a distance of d1, it is shifted to a distance d2 using a micrometer. So while you shift the mirror, what you see is in the telescope, you can see a number of fringes getting shifted across the cross wire. Okay, and you have to count the number of fringes. So let the number of fringes be n, that is crossing the field of view. Now we have the condition for the path difference at the central dark fringe as path difference 2d is equal to integral multiple of lambda, that is 2d is equal to n lambda. Here at d1 position, let us take the count of the first fringe as the 0th fringe, that is n starts from 0, 1, 2, 3, etc. So 2d1 is equal to 0 lambda. This is the first equation. Now after shifting the mirror to the position d2, let us count the fringes and we would have obtained n number of fringes. So this condition becomes 2d2 is equal to n lambda. Okay, let this be your second equation. Now, the second equation minus first equation gives us, check, 2d2 minus d1 is equal to n lambda. That is 2d is equal to n lambda. Hence, we can calculate the source wavelength as lambda is equal to twice d by n, where d is the distance moved through the micrometer and n is the number of fringes that have crossed the cross wire in the telescope. Now this is the final equation that is used to measure the wavelength of the source. Now we are coming to the end of the session, so let's go back to the first image that I showed. Now this is the spectrum or a reading that we got that detected, that gave us the first direct evidence of detection of gravitational waves, and it was done using a Michelson's interferometer at two different labs simultaneously. Okay, so we have two labs at Hanford and Livingston in the USA, and both of these laboratories recorded a series of pulses as shown here. Okay, and this was the direct evidence of the gravitational waves. Now, what is gravitational waves? It is defined as it's a transverse wave of very low frequency. Okay, it is not like sound. Its frequency is defined below 10 raised to 4 hertz, and we can only measure its amplitude. Now, these gravitational waves is identified to be originated from the coalescence or emergence of two black holes millions and millions of light years away. Okay, so when that cosmological event happened, the space-time fabric, okay, that is the space-time curvature, it got ripples in it, and that ripples have traveled across millions of light years and have reached us as feeble gravitational waves. Okay, so we are able to detect such an event by using a Michelson's interferometer. Okay, so this was done in the year 2016, and studies are still going on from the readings obtained from those cosmological events. India has also contributed a lot with the LIGO India project. And why I'm saying this is this instrument has a lot of significance in doing several studies. We can do imaging techniques using Michelson's interferometer. Okay, so there are a lot of applications using Michelson's interferometer, and it is important that you learn it. Okay, well, that's the end of today's session. Thank you.